Hey guys, welcome back. My name is Miss Danielson, and today we're doing an introductory lesson to quadratics. This is easily the biggest topic in Year 11, and it's involved in almost every other topic, so it's the best place to start. The format for a quadratic we have seen before is ax squared plus bx plus c. That's where a, b, and c are numbers, but the important thing about quadratics is that they've got an x squared term, an x term, and a number term. So generally a three-term expression. Now don't confuse quadratics with linear expressions. Linear expressions we've been seeing since year 7, and they're pretty straightforward for you by now. Quadratics is a completely different way of working with expressions. Okay, you will recognize this expression here, hopefully, mx plus c. Because if I say y equals mx plus c, you should be thinking the equation of a line, where m is the gradient and c is the y-intercept. We'll look at the graphs as well in a minute, but I first want to have a look at the algebra behind it. Linear equations can be rearranged to find the solution, and it's just a single solution. So when I've got an equation like 4x minus 7 equals 5, and I want to find out what x is, I can rearrange that to get x by itself by moving all the other values to the other side, and when x is alone, I know its solution, I know its value. So starting by moving the 7 across, it's minus, so I'll take it across, it'll be plus. Then I'm going to move the 4 across, it's multiplying by the x, so I'm going to take it across and divide. And that gives me my one and only possible answer for x. In this equation, x must be 3. That's the only possible value that x could have that would make 4x minus 7 equal to 5. Right? You can try substituting into that for yourself if you like, and you'll see that that gives an answer of 5. But this, again, is very basic. We've been learning this for years now. Quadratics are different. Let me show you a quadratic. First of all, it's not possible to solve quadratic equations by rearranging. You can't get x on its own. Here's an example of a quadratic. X squared plus 7x plus 10 equals 0. Now hit pause if you want and try and get x on its own. I promise you it's not possible. If you're trying to group your x squared and your x together and then send everything to the other side, you can't do that. They're not like terms. If you're thinking to get rid of the square, you'll just square root. That would get rid of the square on the x squared, but it will leave everything else under a square root sign, including the 7x. So you can't get rid of that square and then group the x squared and the 7x together. It is not possible to get x on its own. It's not possible to solve that way. Quadratic equations need to be factorized to solve. Now, factorizing we have seen before. That means finding a value or a variable that you can divide things by. And when you factorize something or you divide any value, you have an answer, which is also a factor. So those are factor pairs. When we factorize a quadratic, we generally end up with a pair of answers. Let me just show you graphically what I mean by this. Here's a linear equation, and you should be able to see that in a linear equation, there is only one x value for every y value. This linear equation in particular, y equals mx plus c, is y equals 2x plus 1. And you should recognize that from year 9 when we've got the equation of the line. The 1 here, the value that's added on, is the y-intercept. That's the c value, where line crosses the y-axis. The number that's multiplied by the x, so in this case 2, is the gradient, and you should see that on this line. Every step we go out to the side, we go 2 steps up. Or we could say that we rise 2 every time we run 1 across. Any way you look at it, that's got a gradient of 2 and a y-intercept of 1. Now, for every point along that line, there's an x-coordinate that goes for every y-coordinate. So if I were to change this formula for the line into an equation where 2x plus 1 is equal to some number, you could rearrange that equation to find out the x value, or you could just look on the graph and you can say, for that y value, what would x have to be? So for 2x plus 1 equals 3, so that's this line here, but I've put y as 3. I can see on my graph, when y is equal to 3, the point on the line is this one here. That's the point 1, 3. So if I were to algebraically rearrange this and solve this and find out what x is, I would find that x is equal to 1 when this equation is equal to 3. So rearrange that and try it for yourself. Okay, for the next one, I've got the same equation of the line, but I've changed the y value for 1. So instead of y, I've got 1. 2x plus 1 is equal to 1. And y is equal to 1 on this line here at this point. That's the point 0, 1. There is only one possible x value that I could substitute in here to make this equation equal to 1. And you can rearrange it algebraically to see it, or I can see it directly on my graph there. There is no other way I can find a point on this line where the y-coordinate is 1, except for where the x-coordinate is 0. There is no other point on this line where the y-coordinate is 3, except for where the x-coordinate is 1. Okay? Quadratics, on the other hand, are not straight lines, and we have graphed quadratics before. They make these parabolic shapes. This is a positive parabola, so here is the assumption that the number in front of the x squared is positive. If a were negative, then I'd have a negative parabola. It would be upside down. It would be a frowny face. Okay, but just for the sake of looking at the graph and understanding why quadratic equations have two possible solutions instead of just one, or maybe none, is because of the shape of the curve. Now notice that there's not a solution for all y values. Y values down here or below, for example, they don't come onto the curve at all. There is no way that I can set a quadratic equation like this equal to negative 20 in this case and find x values that would make that true. It just wouldn't be true. There are no solutions. However, most of the y values have two possible x values that give that y value. Let me show you here. Those 2 points on the curve are 2 points in line with where y is equal to 0. So if I had a quadratic set equal to 0, I would see that there's two possible solutions. X might be -5 or x might be about 3, I would say. We could solve it exactly algebraically. This is just for the sake of seeing in the graph there are two solutions. Or if I tried another y value, if y is equal to -10, there are two possible x values in the quadratic equation, whatever that equation is, that's equal to -10, there would be two possible x values that make that true. Or if I said when the quadratic is equal to 20, well, there's one point here, and quadratics make symmetrical parabolas, and the rule goes on forever. So even though I haven't drawn it, there would be another solution over here as well. So usually there are two solutions, a pair of solutions, just like the pair of factors that we're about to find when we factorize. Okay, so now looking at the format of a quadratic algebraically here. Don't let the graphs confuse you. Let's just look at the numbers. To see where a quadratic comes from, it's got an x squared term, an x term, and a number term, where a, b, and c could be any values. However, we need to have an x squared term, or this would no longer be a quadratic. If I let a be equal to 0, as I have down here, I can simplify that, and that would just be a linear equation. The x squared would disappear, and I've got 4x plus 7. If the x squared term is missing in the quadratic, it is no longer a quadratic, and it becomes a linear expression. And we can deal with the linear expressions the same way as we always have. So let's look at a real quadratic here. Here, I didn't let a equal 0, I let a equal 1. Don't get that confused though. If I have 1x squared, I don't need to write the 1 in front of it. I can just write x squared, right? You don't need to write the 1 in front, but don't think that that means 0x squared. This is definitely a quadratic. It definitely has an x squared term, an x term, and a number term. Okay, this is the most common type of quadratic that we're going to start out with. 3 terms, x squared term, x term, and number term. And when I've got a equal to 1, so there's no number in front of the x squared term, it makes it a little bit easier for me to factorize because I just have to remember one thing, and that is that x squared is the same thing as x times x. So when I factorize, when I set up my two sets of brackets, I have to remember that each of those brackets needs to have an x in it, so when I multiply them together, they make x squared. Right, now to understand how to factorize, we might as well just work backwards from this and remember where they come from. So let's start out with this. That is our goal here. We want to turn a quadratic into this. This is the factorized expression because I've got it set out as a bracket times a bracket. Each of those brackets is to be considered as a factor of the quadratic. Now we remember how to multiply brackets out. We do the first term times the first term, and then the first term times the last term, and then the last term in the first set of brackets times the first term, and then last times last. Multiplying all that out, that would be x times x makes the x squared, x times the 7 makes 7x, 4 times the x makes 4x, and 4 times the 7 makes 28. And the signs are important here. Here everything is positive, here everything is positive. We will get into negatives and it will get a little bit tricky. You need to make sure you're paying attention to the signs. Okay, so that's my expanded out brackets. However, this isn't exactly the format that I've been talking about. I've got an x squared term, and I've got two x terms, and then I've got a number term. But surely you remember that we can group like terms together, so I can simplify that. And that makes 7x plus 4x is 11x. Remember where that came from. This is now in the right format. I've got an x squared term, an x term, and a number term. The x term, the one in the middle, came from adding together the two terms in the middle there. And the last term, which I really haven't changed here, but remember where that came from. The 28 came from multiplying those two numbers together. So when we're factorizing, remember where all this came from. Two numbers added together to make 11x and multiplied together to make the 28. Right? So two important things to remember. You need two numbers which multiply to make c, that's multiply to make the last term, and the same two numbers have to also add to make b, the middle term. Okay? So let's try an example of like that moving forwards. Here's a quadratic. I've got an x squared term, an x term, and a number term. And I want to write that in the format of a bracket times a bracket. First thing to remember, what's going to make this easy for us, is that a is equal to 1 here. There is no number in front of that x squared. And I know that x squared is the same thing as x times x. So I start with my brackets. X in one bracket, x in another bracket. Right, now we need to think about our numbers. The numbers that go in these brackets with these x's need to be two numbers which multiply to make c. C is our last number, that's the 18, the one that's on its own, and add to make b. B is our middle number that goes along with the x. Okay, so two numbers that multiply to make 18 and add to make 9. Big hint here, don't start by thinking which numbers add to make 9. There is an infinite number of pairs of numbers that add to make any value. But there is a set number of pairs of values that multiply to make any number. You can do a factor spider to see those pairs of values, and you'll see that you will run out of pairs. So start with the factors. So my factors of c, my factors of 18, could be 1 and 18, or 2 and 9, 3 and 6, and I think that's it. So do any of those pairs add to make b? Do any of those pairs add to make 9? 1 and 18 is 19, 2 and 9 is 11, 3 and 6, that makes 9. So those are my pairs of values. The sign is important. So when I put them in the brackets, I'm going to put positive 3 and positive 6. Or you could put positive 6 and positive 3. Doesn't matter the order as long as you've got the right numbers and the right signs. We don't want to put negative 6 and negative 3. Okay? Now, just to check if that works, because you could very easily have put the wrong sign in there or got the wrong numbers. So let's just multiply it out. I'm going to do a mental check here. It doesn't need to get written down, but you should always do it. So if I do x times x makes x squared, good. X times 6 makes 6x. 3 times x makes 3x. And 3 times 6 makes 18. Now, these middle two terms need to add together to make my middle term, which is 9x, and 6x plus 3x does make 9x. So I'm happy with that. Good. Again, our answer is this in the red box here. Either this pair of brackets or that pair of brackets. You don't need to put both of them in this case. The important thing is that you simply found the factor pair that would multiply to make this quadratic. Now, this has been an introductory lesson to quadratics. Please join us for our next lesson, where we'll go into a few more examples of factorizing three-term quadratics, and I'll leave you with a practice exercise that you can try for yourself. I hope you found this lesson helpful and interesting, and you'll join us for our future lessons on solving quadratics. Until then, keep practicing, and I'll see you soon.